Chapter 6. Circular Motion and Gravitation. So we already talked about how radial acceleration is given by the velocity squared over the radius of the circular path. And we know that the acceleration can still change based on the change in direction of the velocity. So even if the velocity is constant, if it's changing direction, then you can still have an acceleration. If we have something that's constantly moving in this type of circular path where the velocity is always constantly changing in the same amount, we call this uniform circular motion. In this case, the acceleration points towards the center of the circle, perpendicular to the velocity. Again, we know the radial acceleration from chapter 3, and so what we have is something moving in a circle like this. Now, because we know that it's moving in a uniform circle with the same velocity around the circle, we can determine the velocity of the object by finding the circumference of the circle divided by the amount of time that it takes for the object to go around. And thereby we can rewrite the expression for the radial acceleration by plugging in this version of the velocity and simplifying. So if we square the top, we get 4 pi squared, r squared divided by r, which just gives you r, and then t squared in the denominator. As with other accelerations, the radial force can be determined using Newton's second law. Now this is not an applied force, where something's pulling on it necessarily, but it is the force that's equal to the mass times the acceleration of Newton's laws. So for example, if we know that something's moving in circular motion and we know that something's pulling on it, the pulling force is going to be the sum of the forces. And then the equals ma part is the equals mv squared over r part. That's the major difference here, is that when we talk about uniform circular motion, it's equal ma, but that equal ma is equal mv squared over r. Again, if we have multiple forces, we have to treat those forces as vectors when we find the sum. For example, if you have a ball that's spinning on a string, the tension in the string provides a force that pulls on the ball, and that tension would be equal to mv squared over r, as the ball was moving in a uniform circular motion. Now, if that string were to break and all of a sudden that force is gone, then the ball would no longer spin in a circle, and it would instead travel in a straight line from the moment that the string breaks. The radial force is sometimes referred to as the centripetal force, just referring to the fact that it points towards the center of the circle.